Hello viewers, good evening. Professor T. N. Oza here. Today I am going to present to you a new video, solution of Schrodinger wave equation for hydrogen atom. In few earlier videos, we have discussed about Schrodinger wave equation, derivation, postulates of quantum mechanics, and its solution for several problems where it can be solved exactly. Today, we will be taking up the last problem, which can be solved exactly, that is hydrogen atom and hydrogen-like atoms. So let us begin. For easy understanding, we have divided the whole video into these points noted over here. Easy points. Introduction. The Schrodinger equation can be exactly solved just for few cases, such as particle in a one-dimensional box, particle in a three-dimensional box, simple harmonic oscillator, a diatomic rigid rotator, and hydrogen-like two-particle atoms like hydrogen atom itself, helium monopositive, lithium dipositive, etc. Solutions of the equation for the hydrogen atom provides information about the electronic cloud surrounding the atomic nucleus and generating the concept of angular momentum as the atomic orbitals. It also helps understand the atomic emission spectrum. Further, it also validates the Heisenberg's concept of indeterminacy. For a clear understanding of this topic, let us begin with the essential features and characteristics of hydrogen atom, which service the diatomic rigid rotor, for example, called hypothetical AB molecule. The first point of comparison of the two is that both the diatomic rigid rotor and the hydrogen atom contain two particles each. For such cases, convenient way is to replace the two separate masses by a single term called the reduced mass mu. For example, of the hypothetical AB molecule, reduced mass is given by the well-known formula mu AB equal to product of the two atomic masses divided by the sum of those masses. Thus, for hydrogen atom, we will calculate reduced mass using the formula product of mass of proton and mass of electron divided by sum of these two masses. The masses of protons and mass of electron are reproduced here for easy reference. Another point of comparison is that for the rigid rotor AB, the bond distance RAB is considered to remain constant. Hence, the wave function for the rotor is a function of two polar variables, theta and phi. Both are angular variables, also called polar variables. But psi does not depend on bond distance, which is constant. But for hydrogen atom, the wave function psi is a function of three variables, r, radial variable, theta and phi, both are angular variables, r being the position vector. Therefore, we can write as question 1, that is psi is a function of r, theta and phi. We can write it as the product of three separate wave functions, r of r times theta of theta times phi of phi. This is called separation of variables. Here in this case, there are three variables. So, in order to solve the Schrodinger equation, we need to separate the variables as three separate parts. Each part depends on one variable. Yet another point of comparison is that for the rigid rotator, we assume that no external force is acting on the body, and therefore the potential energy term V is arbitrarily set equal to zero. But for hydrogen atom, it is not zero. Its value is minus ZE square over 4 pi epsilon 0 R. Here Z is the number of protons in the nucleus, one this in this case. P represents the unit of electrical charge. 4 pi epsilon 0 is permittivity of the vacuum. R is, I told earlier. You can consider R similar to something similar to radius, although it is position vector. How this expression comes is given in equation 2. We have to integrate dV within limits r equal to infinity to r equal to r, one distance. And note that integration of r power minus 2 with respect to r is minus 1 upon r. That's how the equation comes. Note that the potential term V does not depend on the spherical angular variables theta and phi. It depends on the variable r only. Conversion of Cartesian coordinates x, y, z into polar coordinate system r, theta and phi. With reference to figure 1, we can transform the Cartesian coordinates x, y, z into polar coordinates using the formula of equation 3. X is equal to sine theta cos phi, y equal to sine theta sin phi, z equal to r cos theta. Note that x, y, and z refer to Cartesian coordinates. They have been changed into the equivalent polar coordinate system with reference to figure 1. Now we are going to set up Schrodinger wave equation in 3 dimensions. You all must be familiar with this famous equation. Equation 4. It is for a particle of mass m moving in 3 directions, x, y, z. Because here we have taken a 2-particle system, hydrogen atom. So instead of mass, we have reduced mass mu. Equation 4 describes its behavior well. Psi is the wave function. This equation is generally written in many forms using Laplace operator or using Hamiltonian operator. So this Schrodinger wave equation can be written in 7 or 8 different forms. You should try writing all those forms. Hint is given here. Sometimes h upon 2 pi is replaced by h cross reduced Planck constant. So I repeat, Schrodinger wave equation can be written in at least 8 different forms. You should try to writing those forms yourself. Incorporating spherical coordinates in place of Cartesian coordinate system and carrying out partial differentiation gives equation 5. Equation 4 leads to equation 5. Equation 5 is reproduced here. Next, we incorporate equation 3 into equation 5. What is equation 3? Separation of the wave function into 3 different parts. And divide it by r square sine square theta over r theta phi. It gives equation 6. Equation 6 is reproduced here. In equation 6 is very important, very, very important. Note its important feature. On the left hand side, there are 3 terms. And on the right hand side, there is 1 term. The first term on the left hand side depends on single variable r. The second term depends on single variable theta. The third term is a constant and the term on the right hand side depends on single variable phi. So this equation is very, very important. We will solve all these three equations separately and then combine together. Obviously, both sides can be equated with a certain constant m square, for example. We can assume. Thus, we can write minus 1 over phi d2 phi over d phi square equal to minus m square phi of phi. Equation 7. Similarly, the left hand side part can also be set equal to m square. For simplification, equation 8 has been divided by sine square theta and rearranged. The result is equation 9. We put it over here. Solution of the phi equation. On solving phi equation yields equation 10, in which n is the normalization constant. Now we need to evaluate this normalization constant. That is very important step. Normalization can be done following the postulate of quantum mechanics. One postulate of quantum mechanics out of 7 says that the wave function must be single valued at all points. This condition is valid provided equation 11 is valid. Phi of phi equal to phi of phi plus 2 pi. It means expression 2 pi I m equal to 1 or cos 2 pi m plus sin I 2 pi m equal to 1. This is on the basis of Euler's theorem, which is e power x equal to cos x plus I sin x. Equation 12 can be true only if m is 0, plus minus 1, plus minus 2, plus minus 3, etc. So we can normalize the wave function as follows. The normalization should yield unity. So we have taken up this principle to normalize equation and get the value of normalization constant. We determine n equal to 1 upon 2 pi. Therefore, we can write the phi part of the equation, phi part of the wave function as equation 13. Evaluation of theta equation and Nm. We have omitted the intricate mathematical step because most of the bio students will not find it easy to understand. We have directly jumped over to the result. Result is equation 14. And as before, we can normalize the normalization constant NLM. The value of normalization constant is given over here. And using that value of normalization constant, we can write the wave function, theta part of wave function, as equation 16. Epsilon value is mentioned. Evaluation of spherical harmonics. By spherical harmonics, we mean combined equation for both angular solution, that is the phi equation, and theta equation. These are independent of the energy E and potential term V. The equation is equation 17. Where n is equal to 0, 1, 2, 3, and m equal to 0, plus minus 1, plus minus 2, plus minus 3, etc. The spherical harmonics are mutually orthogonal. Solution of the R equation, radial equation. The potential energy term depends on the radial variable R. The effective potential is made up of two parts, attractive part and repulsive part. The solution of R equation yields principal quantum number n having integer value 0, 1, 2, 3, etc. It is this quantum number which determines the energy of electron. The equation is given as equation 18. RH is the Rydberg constant whose value is given. The value of n is any positive number as told earlier. And L is a Mutsar quantum number whose values are 0, 1, 2, 3, etc. up to n minus 1. Complete wave function and shape of hydrogen atomic orbital. Complete wave function means radial part, theta part, phi part, angular part and radial part. The complete wave function for hydrogen-like atom is given as equation 19. Here, s orbital shown. Note that Bohr gave discrete circular orbits, but later that concept could not be accepted. The concept of Heisenberg uncertainty and the principle of probability came into picture. So here these s orbitals contain electronic clouds, not discrete energy orbits. And there is a nodal plane between 2s and 1s. So this is just one figure. In books, many other diagrams are given for all other orbitals. The only thing is quantum mechanics based on principle of probability and Heisenberg uncertainty principle and quantization. So you should remember these things in mind. I hope by 2-3 readings you can understand this problem. In examination questions, the entire problem is not asked, only parts of these are asked. Even if not from examination point of view, for general understanding, you should have the idea how quantum mechanics helps solve hydrogen atom problem. Thank you very much.